Now we will model the medium lines. So what is the length of medium lines? It will vary from 100 kilometers to 250 kilometers. Okay, so in medium lines, what do we take? We take the resistance and inductance in series and capacitance in parallel, right? So here we have two kinds of representations. First one is the nominal T representation. Here what we do is, half of the resistance we keep on one side, in between we keep the capacitance, and the half of the resistance and inductance we are going to keep here. Okay, so here this value is R by 2, this is X by 2, R by 2, X by 2, and this is the capacitance whose admittance we will take as Y. Okay, so we will discuss in terms of admittance only. Okay, now what are the sending and receiving end voltages? This will be Vs, this is Is, the receiving end current, receiving end voltage Vr. Now what will be the current through this capacitor? That is going to be the charging current, right? So that we will take as IC. Now we have to find out the ABCD parameters. So we will write down the voltage and current relations. If you apply KVL in the first loop, what will you get? Vs, this is equal to the drop across this plus the drop across this. So this drop also we will represent, this is Vc we will take. Okay, so Vs is equal to Is into Z by 2 we can take, right? This entire thing is Z by 2, half of the impedance. Okay, Is into Z by 2 plus Vc. Now we want to express Vs in terms of Vr and Ir. Okay, so we will simplify this further. What is Is here? Ic plus Ir. Okay, so here you can write Ic plus Ir into Z by 2. And what is Vc? If you apply KVL in the second loop, then Vc is the voltage drop across this plus the receiving end voltage, right? So here you are going to get Ir into Z by 2 plus Vr. Okay. Now Ic, this you can write as the voltage into admittance, right? So here instead of Ic, you can write Vcy plus Ir into Z by 2 plus Ir Z by 2 plus Vr. Once again we have the Vc term here that we can again write in terms of Vr and Ir as Ir. So here there is extra Y term. So Ir Z Y by 2 plus Vr Y plus Ir whole Z by 2 plus Ir Z by 2 plus Vr. Okay. So now we want to express as something into Vr. So we will first take out Vr common. So what are all left here? Y Z by 2, this term, right? This is Y into Z by 2 plus here you have 1. Okay. So plus 1 plus Ir. Here you have this term and this term. 3 terms you have. Okay. So this is going to be Z square Y by 4 plus Z by 2 plus Z by 2. This you can write as Z, right? So here you are going to get plus Z. Now what is this term? This is going to be A and this is B. So we found A and B. Next C and D you have to find out through this relation. Is you have to express in terms of Vr and Ir. So this we have already seen, right? Here you had Is. Okay. So Is we have expressed in this form. Okay. So this is the value of Is. So this is going to be VRY plus IR1 plus ZY by 2. Okay. So here this value is going to be C and this is going to be D. Now you can write the ABCD parameters. This is VS, IS, this is equal to ZY by 2 plus 1 and B is Z into ZY by 4 plus 1, right, and C is Y, D is ZY by 2 plus 1. You can see that A is equal to D. So it is a symmetric network. We can see from the representation itself, it is symmetric, right? The network is symmetric. So you got A is equal to D. And here you have VR, IR. Now we will see how to draw the phasor diagram. See, the process to draw the phasor diagram is pretty much the same. Just for the sake of practice, we are drawing. Okay. So we can take the circuit here once again. Here you have capacitance, inductance, resistance. This is R by 2, X by 2, R by 2, X by 2. This is C. This is the sending end current, voltage. This is receiving end current, voltage, and this is the charging current. Okay, so this you can represent as the admittance, right? So now what we will do, we will take VR as the reference. VR, we take the reference. That means the angle of VR is equal to 0 degrees. Okay. So here if you are taking VR like this. Now here we need to take the load power factor angle. Okay. So this, for a particular power factor angle only we can construct the phasor diagram. So this is the load power factor angle, which is nothing but the receiving end power factor angle. Okay. So this is going to be IR, which is lagging by angle phi R. Now what will be the drop across this resistance IR into R by 2? This will be in phase with IR. IR X by 2 will be perpendicular. Okay. So here you will get IR into R by 2 and this will be perpendicular, IR X by 2. Now what will be the phasor sum of VR and this voltage drop? VR plus voltage drop across this, it is going to be VC. VC is the voltage across the capacitance. Okay. So here you have VC. Now next parameter that you can represent is IC, the charging current. Okay. So this is VC, the voltage across the capacitor, and IC is the current through capacitor. So what will be the relation between IC and VC? IC should be leading VC by 90 degrees, right? So here you can draw IC. Okay. So what happens next is we need to find IS as the phasor sum of IR and IC. Okay. So you can in fact draw IC here, so that IS you will get something like this. Now what is VS? It is the sum of VC and the drop across this. We know VC. Now how do we find the drop across this? With the help of this IS vector. Okay. So parallel to this IS, you have to draw here from VC. Okay. So this is IS into R by 2, and here at 90 degrees angle you are going to get IS into X by 2. And now if you add this VC, IS R by 2, IS X by 2, you are going to get the sending end voltage Vs. Okay. So this is how you construct the phasor diagram. Okay. It's just a little bit of practice, it's actually pretty simple. Okay, and one more parameter that you can represent here is the angle between this Vs and Is. What will it be? It will be the sending end power factor angle, phi s. Now a few more points here with regard to the T representation of medium line. The voltage regulation is going to be same, Vs by A minus Vr divided by Vr, this is at full load, okay, into 100. This is the percentage voltage regulation, okay, this is not subscript. Next, what will be the total three-phase losses? This is going to be Is square R by 2, 3 times of this because there are 3 lines, plus 3 times IR square R by 2. This will be the total 3-phase losses. If it's only for one single phase, that means per phase, then you just remove the 3. That's all. Okay. Then the next point is the efficiency. So this is the receiving end power divided by the receiving end power plus the losses. Okay. And at no load, IR is equal to 0, but Is is not equal to 0, it is equal to what? The charging current, which is IC, okay, and this will be equal to C times VR, okay. This is, you can write IC is equal to, Is is equal to IC is equal to C into, if you remember the first equation, Vs is equal to AVR plus BIR. Now when IR is 0, Vs will simply be equal to AVR, right? So here you can write VR, instead of VR you can write Vs by A, okay. So this is how, this is the relations when there is no load, there is no load connected. The next kind of representation of medium lines is the nominal pi representation. So in the previous circuit, the circuit looked like a T, right? So here it will look like a pi, okay. So here you will have the capacitance, this is divided into 2 equal parts, and the series parameters are intact, okay. So this is going to be R and this is X. This is the sending end current, sending end voltage, and here you have Y by 2, Y by 2. We have divided into 2 equal halves. So this is the receiving end current and voltage. Now these currents also we will take, this we will take as I, and this is the charging current at the sending end side. This is charging current at the receiving end side, okay. Now at the input side you can write KCL. Previously we applied KVL, okay, but here we will use KCL. So Is is equal to ICS plus I, right? But what is ICS? This is the current through capacitor. So ICS you can write as the voltage into admittance. So what is the voltage here? Vs, and admittance is Y by 2. Next, what is I? I, if you apply KCL here, I is equal to IR plus ICR, right? So IR plus ICR, okay. Further ICR you can write as, this is Vs by 2 plus IR plus ICR you can write as this voltage into this admittance, okay. So VR Y by 2, this is V, this is what you will get. This we will take as equation 1, okay. Now what we want in terms of VR and IR. Is we want to express in terms of VR and IR. So we will see what is Vs. So Vs, if you apply KVL across this loop, what is it going to be? Here Vs will be across this. It is equal to the drop across this plus the receiving end voltage. Okay. So Vs is equal to Iz plus VR. Now we already saw what is it? IR plus VR Y by 2 into Z plus VR. Okay. So here we got Vs in terms of VR and IR. So what will this be? You can write this as VR, you can take out common, which is going to be 1 plus Yz by 2 plus IR into Z. Okay. Then what is the A term? This is A, 1 plus Zy by 2. And what is B? B is simply Z. Okay. Now this value of Vs, if you substitute in equation 1, this is equation 2. If you substitute this in equation 1, you will get equation 2 in equation 1 gives Is is equal to, I am writing the final expression here, VR into Y, Zy by 4 plus 1 plus IR into Zy by 2 plus 1. Okay. So this you can take as the third equation. So here itself you have C. This is C and this is D, right? So now we have the ABCD parameters, Vs and Is. This is equal to, A is 1 plus Zy by 2, B is Z, C is Y into Zy by 4 plus 1 and D is 1 plus Zy by 2. And here you have VR and IR. Now let's see the phasor diagram of nominal pi representation. Okay. So you can redraw this for the sake of reference here. This is Is, Vs, here you have the receiving end current, voltage, this is Y by 2, this is Z, and this current is I, this current is ICS, this is ICR. Okay. So here also, just like in T, we will take VR as the reference. So VR is going to be horizontal line like this. Okay. And we will take the load power factor phi r. Okay. So load power factor angle. So here we will take it as lagging. Usually the loads are lagging. You can try out for the leading loads as well. Okay. So here we will take at an angle phi r, we will take current, receiving end current IR. Now we want to draw the voltage drop across this impedance, right? So in order to draw that, we first need to identify the current I. So what will be I? I is equal to the receiving end current IR plus ICR. So first we need to find ICR. Now this is the capacitor, the voltage is VR. So the current through capacitor is going to lead VR by how much? By 90 degrees, right? So here you are going to have the current at a 90 degrees angle with respect to VR. So this is ICR. Okay. The same thing if you draw here, then the phasor sum of IR and ICR is going to give you what? I. So here you can draw I. Okay. Now once you get I, then you can draw the voltage drop across the resistance and inductance. This is R and this is X. Now I into R is going to be parallel to this. We have to draw here. So this is going to be I into R, and perpendicular to this I into X. Now if you add VR, IR and IX, what you're going to get? VR plus the drop across this is going to be nothing but the sending end voltage. Okay, so here you can draw the sending end voltage Vs. What else is left out here? Only the sending end current. Okay, so now Vs we know, sending end voltage. Is will be equal to the sum of I and ICS. So first we have to draw ICS. So ICS will be leading Vs by 90 degrees because it is the current through capacitor. Okay, so this you can take as ICS. This angle is going to be 90 degrees. Now you can add this. This is I. You have to add with this ICS. So you can draw here. This is ICS. So you are going to get IS here. Okay. Now what will be the angle here? This is going to be phi S, the sending end power factor angle. Now the voltage regulation, it is same, Vs by mod A minus VR full load, because this is the standard expression, right? For short line we derived a simpler expression, but for medium line it is the same expression only. Okay, and what about the line losses? The three phase line losses, this is going to be 3 times I square R. Okay, if it is single phase, then you simply remove this 3. It is simply going to be I square R, and efficiency is same only, PR by PR plus PL. So this is the losses. So we have discussed 2 models for the medium lines, and one important thing here is these models, these 2 models that we have discussed, they are not equivalent. Okay, pi and T models are not equivalent. So equivalent means if you do some manipulations, transformations, then you should be able to get one model from the other, but that is not the case. The pi model, it looks like delta, and T model looks like a star, right? So if you think that you can get this by star delta transformation, that is not the case. Okay, so star delta transformation is not applicable here, simply because they are not one and the same. They are just 2 different ways of representing the medium length transmission lines.